So hi and welcome everybody. Welcome back to the lecture of wireless security course. So following up from where we left off last lecture, we talked about the need for new alternative security solution to the existing cryptography approaches. And we mentioned the key challenges associated with cryptography and why we need new different solutions, and mostly the solutions related to physical layer security. Now this is to show you that how cryptography is going against the requirements of future services. So we all know from the 5G course and the 5G technologies that we will have in the future three main services. The first one, if you look at the left-hand side figure, a triangle, you can see that we have three main services. We have the massive machine type communication at the bottom left side of the triangle. We have the ultra reliable low latency communication, which is at the bottom right side of the triangle, and the top side of the triangle, at the tip of the triangle, we have the enhanced mobile broadband. And if we look at these services, we will notice that each one of these services has a certain requirement that's going to conflict with the cryptography, because cryptography and the current security approaches are based on making things complex. The more complex it is, we assume that the more secure the algorithm will be. So if we look at the massive machine type communication, what's the requirement that's conflicting with cryptography or complex cryptography? We have the low power consumption and the battery limited devices and processing limited, storage limited devices. Massive machine communication is all about sensor networks, smart city devices, and you know, these tracking devices and measurement sensors and things. So we can clearly see that the requirements of this service is conflicting with the requirement, with the nature of the cryptography algorithms. If we go and look at the ultra reliable low latency communication, we can see that one feature of this service is the low latency. And this is obvious that it's conflicting also with the cryptography, because cryptography will increase the latency. Why? Because of the processing time it takes for encryption and decryption, and because of the signaling overhead. You need to share ahead of the time a key and wait for handshaking and so on. If we look at the third service, which is enhanced mobile broadband, one of the key requirements for this service is to improve the throughput. Why we need to improve the throughput? Because we have applications like extremely high data rate file transfer, 3D video, 4K screen. We have streaming, ultra high definition streaming. We have gaming. We have augmented reality, and so on and so forth. One of the key requirements for these applications is the high throughput, and the high throughput can be achieved if you reduce the latency and reduce the complexity and process your data faster. This is how you can achieve high throughput. Yeah, aside from the bandwidth and this, but you need to process things faster with minimal delay. So obviously from these requirements, one can see clearly the conflict between the requirements of the future services and the intrinsic features of cryptography. This is what motivates finding new alternative solutions that can really solve these challenging problems. And this is the Internet of Things scope that, as you can see, it can be integrated with each and every part of our life. It's a horizontal technical thing that can be embedded with so many different fields, starting from vehicle asset and bit monitoring and controlling, like smart parking, onboard diagnostic systems, sharing information on the board, in the agriculture industry as well, smart farming, preparing the soil, monitoring optimal condition for planting, energy consumption, security and surveillance, including smart bulbs, smart domotic systems, building management system, machine-to-machine wireless sensor networks, smart homes and cities, telemedicine and healthcare. All these are sectors that are going to be using Internet of Things, which means that Internet of Things is a key component, a key technology component that's going to be adopted by so many sectors. And the problem with the Internet of Things, it's security. And to make Internet of Things a reliable solution and something that we can depend and rely on, we need to fix its security issues. We need to fix the security problem in it. And fixing the security problem cannot be with just making things more complex to ensure their security, because of the characteristics and requirements of these devices, which are different from base station, for example, that's always connected with an electricity power source. It can consume as much as it needs, and it has infinite processing capabilities. It can contain servers of powerful resources, but this is not the case when you talk about a small, tiny Internet of Things device. And if you look at the 5G as well, you have also thin devices. These thin devices, of course, are going to be limited in processing capabilities. You have the requirements of 5 millisecond latency, which is also against the requirements of, against the the features of the cryptography approaches. And you have the cloud. You need the cloud to be closer to the user. You need the cloud to serve the user quicker, immediately, without any latency, without any delay. And you have the content, which is HTML produced, and there are really many companies around the world that are specialized only in optimizing the content in such a way that it can display to your device as fast as possible. So all these are justifications and proofs that show the importance of adopting a new alternative security approach that can fix the weaknesses and drawbacks and flaws of cryptography approaches. So what's the solution then? A promising solution that can fix some of these problems, I'm not claiming all, some of them, is physical layer security based approaches. And not any of them. There are some specific techniques that can be really helpful in addressing the challenges we talked about. So, and the way that this physical layer security approach should be designed is to secure the data on the signal level, not on the bit level. So we are talking about the signal level. So at the signal level, the eavesdropper should not be able to decode, not only at the bit level. So once there is not enough SNR for the receiver to detect or decode, then what's the point of trying exhaustive search process? There is no need for this, because the signal to noise ratio or the signal power is not even enough for the eavesdropper to see the message, to detect it even at the hardware level, at the physical layer level, RF chain level. This what makes physical layer security a powerful solution, powerful alternative, promising candidate that can really fix some of the issues related with cryptography. And what are the main three problems that physical layer security is expected to solve? The main three things are eavesdropping, which is intercepting and monitoring the traffic, like the experiments we have done with the Wireshark software, monitoring the traffic and this, but even eavesdropping, knowing the message itself that's being communicated. Second is jamming and emitting, and then spoofing or impersonating. So we need to make sure that the approach that we come up with can really have solution for all these threats, all these critical breaches: eavesdropping, jamming or interference, and spoofing or impersonating. as you can see on the left-hand side figure here, where you have a legitimate transmitter called Alice trying to communicate with a legitimate receiver called Bob over a TDD channel, time division duplexing channel, and you have an attacker. This attacker is called Eve here, but you can name it whatever you like. And we want to make sure that Eve cannot intercept or monitor or get access to the messages being communicated between Alice and Bob. And also, if Eve jams, Alice and Bob should be able to handle this jamming and should be able to cancel it and overcome it. And more importantly, if Eve tries to spoof or impersonate, spoof Bob in the eyes of Alice or spoof Alice in the eyes of Bob, they should have a mechanism to overcome this. And this is happening all at the wireless signal, at the physical layer. This is not something at the application or network. So that's the difference between the other attacks that exist maybe at the TCP/IP protocol layers. And one thing to point out here is whatever you design here, yes, you are trying to design something that can protect the data in move, in transmission, the data that's being communicated or transferred. But you can apply the same thing, more or less, also on the data that's being stored in a hard drive or cloud. And I believe this is so critical as well, as critical as the data in move, because our data is going to be stored on the cloud, all of us, and we need to make sure that this data stored in the cloud only accessible by us, by the people who owns it. And we don't want this to be accessible by anybody else. So how can you do this? By bringing innovative ideas and solutions that can work at the physical layer, maybe, which makes things harder and more robust. So this slides gives you a basic system, presents to you a basic system model of the physical layer security system, where you have a node called Alice trying to communicate with a node called Bob securely from a node called Eve. And this node called Alice, it has a secret message, it encodes it, converts the message from M to X, and this message goes, this signal goes through a main channel called Bob's channel, and then when it reaches the receiver Bob, the receiver Bob tries to get the message from the signal it receives, which is RB. And for Eve, Eve is assumed to know the algorithm, the security algorithm perfectly, and he receives the data through his channel, which is assumed to be different from the channel of Alice to Bob. So the channel from Alice to Bob is different from the channel of Alice to Eve because of the spatial correlation property of wireless signals. If you have taken wireless communication course with me in the previous semester, or you will take it in the coming semester, you know that the channel changes based on the location, based on the environment, based on the reflections. And by changing the location of the device by half wavelength delta, you can expect to have different realizations of the channel. And this means that different channel response, different channel in time and frequency, and makes the property completely different. And this is one of the assumptions that we assume in physical layer security, and it's physically it's the physics behind wireless transmission, and this is true so far. I mean, unless you can produce an algorithm that can break this assumption. In this case, you might need to finding different solutions that can overcome this assumption. The other assumption we usually make in physical layer security, or many papers consider, which is not so critical, by the way, you don't need to assume it, but mostly it facilitates the implementation of some physical layer security methods, is the TDD assumption, which means that you assume that you are transmitting your channel in a time division duplexing mode, where the downlink transmission is using the same frequency as the uplink transmission, which means that the channel response in the uplink is the same, more or less is the same as the channel response in the downlink. This triggers the idea of using the channel between the transmitter and receiver as a common source of randomness, where they can extract shared information that are secure and only known to the parties involved in the estimation of the channel. And this solves the problem of key management that we talked about at the beginning of the lecture, where we said one of the key problems associated with the cryptography is the key management and distribution process. So if you, in this case, if you can extract some random keys or random things from the shared wireless channel between the transmitter and receiver, then you don't need to have any third-party node or third-party device responsible for sharing and distributing the keys. So you end up you end up with two advantages. The first advantage, you don't need key sharing and third-party node that sometimes you don't trust. And the other advantage, you reduce the signaling overhead, which means you improve the performance of your network. So this is the model basic. This is very basic model actually. It's not so complex or sophisticated. It just, we simplified it so that you can understand it and you can get some sense of how things can work here. Now, if we look at the physical layer structure here, the big picture of physical layer security techniques against wireless passive eavesdropping, we have two pictures. The first picture to the left-hand side and the right-hand side. These two pictures like summarize clearly and briefly the physical layer security domain. So we have the techniques that exist in this domain can be classified into two approaches. We have the approach called signal to interference noise ratio based approach. We call it the keyless approach, where you don't need to have any key for transmitting your data securely. And we have the complexity-based key approach, where you depend on using keys which are extracted from the channel to secure your transmission. Now, it's worth noting here that the cryptography approaches, most of them are always dependent on using complexity-based key approaches. So the new approach that physical layer security gives to us is the keyless approach, which is the signal to noise ratio based approach. Now, what's the concept behind this? The concept of SINR based approach is that if the noise or fading or interference at the eavesdropper is made higher than BOP, then one can design a transmission scheme that can ensure security without using keys. Okay, this is the main concept of this approach. So what's the goal in this section, in this direction? The goal is to make sure that the noise level or fading or interference in the link with respect to Eve is larger than the link with respect to BOP. BOP should have clearer channel, noise-free, fading-free, interference-free. And how you can achieve this? You can achieve this by two things. You can either have a natural channel that have this that can meet this requirement, or you can intelligently and artificially design the channel with respect to BOP to be stronger in terms of the signal to noise ratio from that with respect to Eve. What about the complexity-based key approach? The concept here to extract random keys from the channel of the legitimate parties to manipulate the data on a bit or symbol level basis. So what you do here is you use the channel, the shared channel between the transmitter and receiver as a common source of randomness and each party can estimate or extract some random bits from this channel and use these random bits as keys, and they can change them as many times as they want, as long as the channel can change. They can estimate the channel again and extract new random bits and use them for encryption and decryption. What are the enabling technologies for the keyless approach? We have channel coding, we have adaptation based on POP's channel feedback, we have addition of controllable interfering signals. So basically, we have the coding approach, the optimization and adaptation approach, and the interfering signal approach. For what about the keyless, the key approach, the key-based approach, what are the enabling technologies? So basically, as I mentioned before, you basically have channel quantization techniques, which exploit channel reciprocity property and its variation at both the transmitter and receiver to extract secret keys. This is how the technology behind these approaches are different. Well, now, if we speak about the merits of these approaches, for the first approach, which is keyless based approach, we don't need to share any keys. There is no need for secret key sharing, which is astonishing actually. Second, it can practically achieve perfect secrecy. Third, processing is at the transmitter side only usually. You don't need something at the receiver to be happening, which is perfect for Internet of Things device, because the Internet of Things device does not need to process anything, and this makes it ideal for its requirements. Fourth, it can save power, enhance efficiency, and as well as the performance of the legitimate receiver POP. All these are exciting merits, exciting benefits, exciting advantages, but also we have some demerits, and those demerits vary from one technique to another. But in general, the demerits are listed as follows. First, the SNR at Eve must be less than the SNR at POP. So this, you don't need to think of it as a demerit, but you can say that this is a requirement for the technique to work successfully. Or Eve's fading must be higher than POP, which is also, you don't need to think of it as a demerit. You need to think of it as a challenge that you need to overcome by designing a proper technique. Third, security is achieved at the expense of capacity reduction. And as you see here, I'm putting like between two brackets, putting 1, 2, or 3 to highlight and point that the demerit here corresponds to some specific techniques here in the second section of this direction. So these demerits are specific only for certain techniques. It doesn't apply to the whole domain. For example, the 2 and 3 here are sensitive to channel errors, which mean adaptation, optimization, and addition of controllable interfering signals. 2 and 3 are weak against eavesdropping collaboration. In this case, where you have multiple eavesdroppers and located in different locations, and all of them collaborate with each other in order to weaken the security method and increase the signal-to-noise ratio in such a way that they can decode the signal successfully. 2, for example, which is optimization and adaptation, cannot achieve perfect secrecy alone. So you need some other techniques, especially the interfering signals, in order to improve the secrecy and make it better. 3 here sacrifices power resources, may increase peak to average power ratio, and degrades POP's performance. 8 requires that degree of freedom at the transmitter is higher than the receiver parties. So these are the merits and demerits associated with the keyless approach. If we go and look at the key-based approach, the complexity-based approach, then the first merit, it solves the key distribution problem and avoids the signaling overhead associated with the key distribution and management process. Second, it provides secrecy even if Eve has better channel condition than POP. The demerits are as follows. Eve is assumed to have limited computing power resources. Key length is limited with the channel variation. Thus, strong secrecy is hard to achieve. in this case, to make sure that you can achieve really very good security level, you need to increase the key length, but the key length is dependent on the randomness that exists in the channel. If the channel is not able to provide enough randomness, then in this case you will not be able to generate enough key rate that can ensure the secrecy of the message. Third, it's sensitive to channel estimation and reciprocity errors. Fourth, secrecy can be broken if Eve is able to know Bob's channel. Fifth, requires processing at both side transmitter and receiver, which results in power delay and overhead costs. Six, it's not very suitable for Internet of Things devices. And here we have a remark, we have a note that each security track or direction or approach has its own pros and cons, merits and demerits. In particular, what may be suitable for some applications, services, systems, scenarios, and channel condition might not be for others. Thus, it's worth devoting some of our research efforts on developing new advanced practical methods that are capable of minimizing the drawbacks of these security tracks and maximizing their merits. So this is general comment regarding the physical layer security domain. If we look now at the right-hand side of the slide and classify these technologies, then we have the keyless approach and the key-based approach, and we have some enabling techniques which we mentioned in the left-hand side of the slide. But now how we classify the techniques here. So we have three main domains: time, frequency, space. And the techniques we will be discussing and talking about in this lecture are related to different approaches, different techniques, but the methods, the physical layer security methods, some of them are going to be designed in time domain, frequency domain, space domain. So for example, for the adaptation based on Bob's channel feedback, we have in time domain, we have techniques like adaptive modulation, adaptive power allocation, optimized waveform, ARQ, pre-equalization. Those are some example techniques that can provide secrecy based on the adaptation approach, which utilize the time domain of the signal. We have the frequency domain of the signal, and example of this is the OFDM subcarrier based power allocation, precoding, and so on. In the space domain, we have the beamforming, precoding, power allocation in MIMO, MISO, CMO, relays, COMB, ASM, SM, DM, DAS. COMB stand for cooperative multiple points. ASM stands for adaptive spatial modulation or angular spatial modulation. SM for spatial modulation. DM distributed. It's for distributed something. M, I forget M for what. It's not for modulation. And we have the DAS, distributed antenna systems. For the addition of controllable interfering signals, we have the time, frequency, space. In the time, we have ARQ with AM. We have CP alignments. Those are just examples. We have hundreds of examples, but here I'm giving just a few examples. Of course, I know that you might not be familiar with these techniques, but we will explain them in the coming lectures, and we will talk about some of them. And the rest are going to be similar with some slight changes. In the frequency, we have OFDM with artificial noise by exploiting CP feature. In space, we have AN injection by exploiting the degree of freedom exists in MIMO, MISO, relay, or COMP. In complexity-based key approach, we have time, frequency, space. In time, you have example on that, exploiting channel variation caused by Doppler and multipath over time. Frequency, you have example on this is exploiting channel variation over subcarriers in OFDM system. And the space, you have example exploiting channel variation over antennas or relays to extract some key bits that you can use as in the encryption process. We have two remarks here. Remark number one, there are hybrid security techniques which use two or more of the above mentioned techniques simultaneously to ensure security in different scenarios. And remark number two is any physical layer security technique proposed in the literature can be classified and fit under one of the above mentioned categories. So this is how you can fit them, classify any security techniques you come across and you read about and you learn, you can put it under one of these categories. So it helps you understand the domain in a much broader way, and you can classify them easily, understand the key ideas behind each one of them. But the point that I want to emphasize here is the fact that there are security techniques that can combine multiple of these together to make it harder for eavesdropper to decrypt and decode. So those are this slide is very important, very critical, and understanding it, especially the left side of it, and understand the merits and demerits and how to maximize the advantages, reduce the disadvantages is very crucial. We have also the secrecy metrics that are used to evaluate the performance of the generated evaluate the performance of the proposed security approaches. We can talk about them in the coming lectures, and we can hopefully also talk about jamming. So I think we can stop here for now, have a break and return, and then continue with the presentations and other things we will do in the next coming lecture. So thank you everyone, and take care and stay blessed.